In this paper, we proposed a 3D visual navigation method for MAV with depth camera based on neuromorphic reinforcement learning named Neuro-Planner. Autonomous navigation in GPS-denied environment is one of the most core issues in the field of mobile robots, especially for micro-air vehicles. It can be used in aerial surveillance, power inspection, disaster relief, delivery, and so on. In the past few years, researchers mainly use global planner and local planner to calculate the path that honor traversability relying on the constructed map. Then researchers design the appropriate controller to track the generated path. These methods meet problems in limited load capacity and unknown environment scenes. Inspired by the reinforcement learning and spiking neural network whose mechanism is more like animal's brain, we propose Neuro-Planner, a hybrid DDPG framework based on TSLIF spiking neurons for MAV 3D navigation. The key idea of Neuro-Planner is that MAV learns a policy mapping states to actions directly by spike neural network. Our Neuro-Planner contains spiking network inference and hybrid reinforcement training. In spiking network inference, the spiking actor network maps the state to the action. The state consists of relative position between MAV current position and goal point, MAV current velocity and visual features from depth image. Then the spiking actor network decodes the state and infers the action. Finally, the action is decoded into setting velocity to implement navigation. Especially, we use TSLIF spiking neurons to form the spiking actor network. We use current and voltage represent the state of the spiking neurons, which have rich spatiotemporal dynamics. In hybrid reinforcement training, we adopt actor-critic networks architecture to help MAV search for an appropriate policy according to the designed reward function. In order to improve the data utilization and make the network converge stably, we also adopt the experience replay and target network mechanisms. Besides, we learn the insight of curriculum learning. We set up a total of 4 training environments, sequentially increasing the difficulty of the environment to speed up training and improve performance. For evaluation, we set up 2 environments to test our algorithm. One is similar to the last training environment, the other is larger and more complex. For training or evaluation, the MAV takes off to a fixed altitude from a random starting point in the ground at the beginning of each episode. In order to demonstrate our experiment result intuitively, we select some evaluation trajectories to show. We first use SLAM technique to map the evaluation environment. We show MAV real-time flying in Gazebo and trajectories in ARVIS. Different from the evaluation environment number 1, which is similar to the last training environment, evaluation environment number 2 is more complex with 21 cuboid pillars. Our algorithm shows strong robustness in the evaluation environment number 2, where MAV meets the unfamiliar environment and unseen situation. For success rate, STBP can reach 4.3% higher than original DDPG in evaluation environment number 1 and 5.3% higher than original DDPG in evaluation environment number 2. Since evaluation environment number 2 is more complex, the success rate of STBP, BPTT, and original DDPG all drop, but the success rate of Slayer stays steady. For average distance and average speed, STBP and BPTT have higher average speed but longer average distance than original DDPG. Slayer performs similar to original DDPG in both evaluation environment number 1 and number 2. The average speed of STBP, BPTT, Slayer, and original DDPG between evaluation environment number 1 and number 2 are similar. But the average distance of these methods all rise since the evaluation environment number 2 is larger. Then all success and failure trajectories in evaluation environment number 1 and number 2 are shown. We show the navigation trajectories in the top view and 3D view respectively. First, we show the success trajectories in evaluation environment number 1 and failure trajectories followed. Secondly, we show the success trajectories in evaluation environment number 2 and failure trajectories followed. In a conclusion, The main contributions of this paper are as follows. Thanks for watching.